All right, AP Chem, we're going to talk about combustion analysis. So let's say you did discover a brand new hydrocarbon, or you didn't know if it was brand new and you needed to identify it. What you would do is you would do a combustion analysis from it. So remember we talked about empirical molecular formulas? When we learned that, we were actually analyzing the results of combustion analysis. So now we're going to learn how to do that. So in this case, we are combusting an unknown hydrocarbon. So usually the problem is going to tell us that it's only compound X consists of only carbon and hydrogen. And how you would do that is you would inject it into a mass spectrometer and it would give you peaks in the range where that's specific to an element. And in this case, the element had only carbon and hydrogen. Because I know it only had carbon and hydrogen, the carbon dioxide, which is 0.686 grams, contains all of the carbon that was in that hydrocarbon. So I use the molar mass of carbon dioxide to change it to moles. And then I can pull the carbon out of there because in 1 mole of carbon dioxide, there is 1 mole of carbon. What that means is if I have a molecule of carbon dioxide, 1 molecule of carbon dioxide consists of 1 atom of carbon and 2 atoms of oxygen. So 1 mole of carbon dioxide consists of 1 mole of carbon and 2 moles of oxygen. So in my calculator, I simply multiply across the top and divide by the bottom, and I get an answer of 0.015587 This is another circumstance where I'm going to carry around a bunch of extra significant figures because of the fact that we're doing an empirical molecular formulas problem and these small numbers can be skewed very easily. Now, let's go to water. Again, if it's a combustion of a hydrocarbon, the combustion reaction always has one of the reactants as oxygen, and that's what it means to burn something. To burn something is to chemically combine it with oxygen. So I'm going to use the molar mass of water to change this to moles of water. And then I can pull out the hydrogen because all of the hydrogen that's in water comes from that hydrocarbon. And this time there's 2 moles of hydrogen in every 1 mole of water. That's because there is 2 atoms of hydrogen in every molecule of water. So multiply across the top and divide by the bottom. And I get an answer of 0.06238899 moles of hydrogen. Now, just like in empirical molecular formulas, I figure out which one is the smallest number, the smallest mole count, and I compare them by dividing. And I will get the subscripts for my empirical formula. So the subscript for carbon is 1 and the subscript for hydrogen is 4. So my answer for the empirical formula is CH4. This time we're going to do a combustion analysis problem that has more than just carbon and hydrogen in the hydrocarbon. So let's read the problem. A compound with a known molecular weight, 146.99 grams per mole, that contains only carbon, hydrogen, and chlorine was studied by combustion analysis. When a 0.367 gram sample was combusted, 0.659 grams of carbon dioxide and 0.0892 grams of water are formed. What is the empirical molecular formulas? So when you burn something that has carbon and hydrogen, you're always going to produce carbon dioxide and water. It doesn't matter if there's other elements. So when I burn this compound that's got carbon, hydrogen, and chlorine, and I burn it in oxygen, it's still going to produce carbon dioxide and water and some other compound that I don't need to know anything about. So we're going to start our problem the same way. We're going to say 0.659 grams of carbon dioxide using the molar mass. I'm going to change it to moles of carbon dioxide. And then I'm going to pull the carbon out of there, pull the oxygen away from it, to find out that I have produced 0.0149739 moles of carbon. I'm going to change this to grams right away because I'm going to have to pull the chlorine out of the original compound, which is multiplied by the molar mass of carbon. I get 0.17984 grams of carbon. I'm going to do the same thing for water. 0.0892 grams of water is formed. And same steps, I'm going to pull the hydrogen out of the water using the molar mass and the mole ratios. To get 0.009882 moles of hydrogen. I'm going to change that to grams right away also so that I can do the next step. So when I add these two together, I'm going to take a second and double check my math on my calculator. And I'm going to add up 0.17984 plus 0.0099592. And that's going to give me the combined mass of carbon and hydrogen together of 0.1897992 grams of carbon and hydrogen combined. So now I can take the mass of the original sample, which was 0.367. That's the carbon, hydrogen, and chlorine combined. I'm going to subtract off the carbon and the hydrogen. Now I'm carrying around a bunch of extra digits I don't need to, but that's no big deal. And the difference between these two is chlorine, which is 0.177201 grams of chlorine. Let's change that to moles. That we do that by dividing by the molar mass. If I divide by the molar mass, I get 0.00499 moles of chlorine. So now we have our moles of chlorine, we have our moles of hydrogen, and we have our moles of carbon. So we're going to do the same thing we did with our empirical molecular formulas is we're going to divide by the smallest mole number. So that would be dividing each of these by 0.004999. So I'll divide each of these by 0.004999. And that's going to give me my subscripts. So here's a 3 for carbon, a 2 for hydrogen, and a 1 for chlorine. So my empirical formula is C3H2Cl. That's the answer for the empirical formula. Now, in order to get the molecular formula, I add up my empirical formula because it gave us the molecular mass. So remember, we compare the molecular mass to the empirical mass, and we get 146.99 given to us in the problem. And we're going to add up 3 carbons with 2 hydrogens and 1 chlorine for a molar mass of 73, or empirical mass, I should say, of 73.496. So that's going to be a ratio of 2. So the empirical formula times 2 is going to be the molecular formula of C6H4Cl2. And that's your answer.